Hey there, math enthusiasts. Ever felt like math is just a bunch of hard work? Today, let's dive into a tale where math becomes our ultimate tool for laziness. Yep, you heard that right. Introducing the protagonist of our story and our lazy friend, Laz. His ideal day comprises snuggling on the couch, surrounded by a mountain of potato chips. Despite his unique skill set, Laz had bills to pay. So, guess what? He landed a gig at the local weather office. And so, for once in his life, Laz was on his feet and not quite lazy. But hey, old habits die hard. Even with the official title of a weatherman, our man could not resist the pull of his favorite pastime, extreme lounging. So, what was Laz's main task? It was to calculate the daily average temperature. Simple, right? Just take the temperature readings throughout the day, add them up, divide them by the number of readings, and there you have it. But oh boy, that sounded like way too much work for our Laz. However, his boss was not so amused. Poor Laz was caught in a storm of his own making. He wondered, how can I do the bare minimum and still nail my job? Under pressure, Laz did what any of us would. He rang up his mathematician friend, Max. Max greeted him with his assuring voice. Laz, forget measuring the temperature all day long. What if you just took a few measurements at specific times of the day, multiplied each of them by a magical number that I'll give you, and summed them up? Voila! You'd have an estimate very close to the real average. And there it was, folks, the magic spell called Gauss-Legendre quadrature, or in other terms, the mathematics of Gauss-Legendre quadrature. Let us take a step back now to understand what quadrature is first. Think of it as finding the area beneath a curve in a specified interval. In the language of mathematics, if the function f of x represents this curve, then this area is equal to the integral of this function from a to b. We can of course evaluate some of these using classical methods, but many functions actually do not have an analytical antiderivative. Moreover, for real life measurements, we often only have specific data points and not the entire function. This is where numerical integration, also known as quadrature, enters the picture. There are many standard methods to perform integration numerically. First up, the rookie, the midpoint rectangular method. Here, we pick points which are equally spaced in the x-axis and build rectangles on each of them with a height equal to the value of the function at those points. Then we add up all the rectangular areas and you've got your estimate for the integral. But remember, with more points, we get a better estimation of this integral. In the limit where the rectangles are all infinitely thin and we have infinite number of them, it actually gives the exact value for this integral because it exactly matches the area under the curve. Leveling up, we have the trapezoidal rule. Now, instead of the rectangle rule, where a constant value is assumed over an interval, a straight line is fit between each pair of points. Still better, the elite Simpson's rule. Now, we use 3 points to fit a parabola. Here, with each advancement, we go from a rectangle to a trapezium to a parabola, and we give more degrees of freedom to the integration, and thus the accuracy of these integral estimations get higher. Finally, the titular Gauss-Legendre quadrature. Firstly, unlike the other methods discussed earlier, this method actually lets us choose the points unevenly spaced. This adds an aspect of flexibility to the method. And secondly, and more importantly, it assumes that the function that is to be integrated can be very well approximated by a polynomial function. One of the underlying ideas here is that the polynomial can be uniquely determined by evaluating the function at some points. For example, a straight line can be uniquely determined by evaluating the value of the function at just two of its values. So, n values can determine a n minus 1th degree polynomial. But as we shall see, this method actually takes it a step further. The general scheme for the Gauss-Legendre quadrature is as follows. If we do an nth order quadrature, we evaluate the function at n points. Then the integral of our function from minus 1 to 1 is given by the weighted summation of the function values evaluated at those n xi points. And these weights, wi's, these are math's magic numbers. Now, if these chosen points are actually the roots of the nth order Legendre polynomial and the weights are chosen carefully, then this method exactly finds the integral for a polynomial up to 2n minus 1th degree. Mind equal to blown. Alright, hold on to your hats now. Let's piece this puzzle together and see how it rescues Laz from his temperature turmoil. Remember Laz's mission? It was to find the average temperature for the day. And if we consider the temperature to be a function of time, then mathematically the average value of the function is given by the integral of the function over the time range divided by the time interval. Math's brilliant suggestion for Laz was to employ the Gauss-Legendre quadrature and those so-called magic moments to check the temperature and the special weights comes directly from the legendary Legendre polynomials. Though a minor tweak needs to be made here since this method is specifically built for an interval of minus 1 to 1, whereas a day spans 24 hours. So now let's set the scene. Imagine a blazing hot summer day in Kolkata. The temperature has been evaluated every 1 hour and the average calculated from that, which is a true average, is 30.30 degrees Celsius. Now, Laz has decided that he can at most measure the temperature 3 times in a whole day. Hence, following Math's method for a third order quadrature, Laz measures the temperature 3 times in that day and crunches the numbers. And from that, he gets an average value of 30.37 degrees Celsius. This estimate is actually very close to the true average value. If we have a look at this plot, but the relative error in the estimation of the average temperature is plotted as a function of the number of degrees of quadrature, we see that even if he was more lazy, so that he only calculated the value at 1 or 2 times in the whole day, he would be still less than 10% away from the actual value. And this is actually the elegance of the Gauss-Legendre quadrature method. Well, you might say that maybe he just got lucky. So let's look at averages now. Now we evaluate this over a month's data. Here, the same thing is plotted but averaged over the whole month. The points here show the average value and the shaded area here shows one standard deviation. From this, we can say that by taking a third order quadrature, Laz on average can be within 2% of the actual value. Now, surely that should be enough to save his job, right? Circling back, our trusty quadrature is supposed to be spot on when the temperature variation is approximated very well by a polynomial of order 2n minus 1. For Laz's third order quadrature, that's a fifth degree polynomial. It turns out that a fifth degree polynomial can fit the temperature data of our day very well, which is why the Gauss-Legendre quadrature is so very effective. End of the day, Lars can lounge and lead in his job thanks to the Gauss-Legendre quadrature. The king of couches emerges victorious, all while keeping it cool or hot, depending on the day. This method can also be useful for cases where laziness is not the issue. In some scenarios, making a measurement can be very expensive or complicated. In such cases, the average value can be computed using this method with very few instances of measurement. So, that's it, folks, for today. Toodles!